Hello everybody. So today we have another lesson of the properties of fluids. Once again, following the previous lessons, we will start from some microscopic features of matter, and then we will try to explain why from our large-scale world, so from our continuum world, the fluids have some specific features. So we have seen last time that the density of a fluid is a function of its position in space and time. However, density depends also on some other properties like pressure and temperature. Now, one very well-known possibility is that the fluid is an ideal gas, and then we know that there is one state equation for ideal gases, which we can write in this way: P by rho equal capital R, which is a constant times T the absolute temperature. Now, be aware that this R is not the universal R, but it is the constant R for the specific gas. So if this is the universal R, we should divide universal R by the molecular weight of the specific gas, and then this uppercase R is the constant for a specific gas. Anyway, from this relation, of which the equation of state is just a very famous example, we see that density depends on pressure and temperature. So let's start to consider the pressure dependence of density. So we start from some volume of fluid. Now we don't distinguish whether the fluid is a gas or a liquid or some fancy solid. And then we want to see how this volume changes when we apply a change of pressure. So we start from the idea that the fluid has a volume V, when the pressure is P. Then we apply a pressure variation, P plus say dP, and then we have a volume variation. Now the volume will not stay V, but will change. Now we know that for a positive pressure variation, there is a negative volume variation. So if we take this volume and we compress it, it has to shrink. So if we want to have here, let's call it in this way, keeping in mind that dV would be negative. And then we have to write a relation between the pressure variation and the volume variation. So a common way to parameterize this variation is that the relative volume variation, so dV by V, will be equal to, actually would be proportional to the pressure variation, but if you want this proportionality to become equal, we must divide by some material dependent factor, which we call E, and then we put a minus here, just because the scientific tradition wants this E to be given as a positive number, dP to be negative, and dP to be positive, and dV to be negative, because the volume decreases. Then if we want a negative quantity to be equal to another negative quantity with E positive, then we must put this minus here. Now, this quantity here is called bulk modulus, or coefficient, sorry, it's not the coefficient of compressibility, which is just the inverse. So, the coefficient of compressibility is 1 by the bulk modulus. Okay, so this is called, this is indicated by E just because it is absolutely the equivalent of the Young modulus for solids. Okay, so what do we learn from this relation? Well, we just learned that the volume variation is linearly correlated to the pressure variation. So if we double dP, we double dV, but we should be very careful because this relation is not really linear because there is dV here. So as long as dP is infinitesimal, dV would be infinitesimal as well and proportional, but if we go to finite quantities, then we have to integrate. And this can be done quite easily because if we make finite these variations, what we can write is that the integral between initial volume and final volume of dV by V, and this must be equal to minus. So I'm sorry, I had a problem with the camera. So this integration, now we can take the second one. So initial pressure and final pressure dP by E. Very good. So now, assuming that E is a number, what we can do is to integrate this relation to obtain the logarithm of final volume divided by initial volume, and this would be equal to minus final pressure minus initial pressure divided by E. Now, of course, this implies that E is a constant. Okay, and this can be easily transformed like final volume equal to initial volume times E to the minus final pressure minus initial pressure divided by E. So, in case E is a constant, the volume decreases exponentially with the pressure difference. So, as you can see, the linear relation holds only for the infinitesimal pressure variations, but doesn't apply for the finite volume variations. Okay, so this is of course a definition. However, E equal to constant is an additional hypothesis. So, is it always true? Well, we could we could run some experiments, and then we would realize that E is indeed constant, at least within common pressure variations for liquids. And it is also a quite large value. We will come later to what kind of value is it. But if we try to do the same for gases, we see that the same does not apply. So the compressibility or the bulk modulus for gases changes with pressure. And then we ask, are we able to quantify somehow this behavior? Well, it is not so difficult, because something we can do is first of all start noticing that when I have a volume and then I start compressing this volume, as a matter of fact, the mass is constant. So I have always the same volume, which I can compress, I can expand, but the mass is always the same. So all the molecules I have in this volume do not leave. Then the mass of the system is constant, and the mass is nothing but the product of density times volume. Now, if this is a constant, if I differentiate, the differential of a constant is 0. And this is a product. So, what I can write is rho dv plus v d rho, and this is the differential of a product function. This must be equal to the differential of mass, which being constant has 0 variation. And this quantity I can rearrange in this way. d rho by rho, this is equal to minus dv by v. It is very easy. It is enough to divide left and right hand side by rho v. Okay, so this implies that this expression using that dv by v is equal to minus d rho by rho, I can write in a simpler way, and the simpler expression would be actually simpler, more useful, would be d rho by rho equal dp by e. Now this minus, which goes here, so I've used in this way, so this minus absorbs this minus here. Good. So what I can do here, well, with this one I can do very little. However, something I could do is to try to manipulate another expression that I could use to derive these bulk modulus. Now we know that all gases undergoing transformations can be described, can be parameterized by the polytropic relation, which is this one. So P by rho to the power k, this is equal to constant. So now, depending on the value of k can be in between 1 and gamma, being gamma Cp by Cv, you can recover all feasible transformations. So when k is equal to 1, you have the isothermal transformation. When k is equal to gamma, which is the ratio between constant pressure to constant value of specific heat, you have an isentropic transformation. Good. So what we can do, we can try to manipulate this expression just to see if we can somehow recover something similar to this one. So let me clean this part of the blackboard. And then what I do, I start by writing that the pressure P is equal to C, this constant, times rho to the power K. Now I differentiate left and right hand side, and so I obtain dP, and this would be equal to C. Now the differential of rho to the power K would be K rho to the power K minus 1 d rho. Now what I can do, I can multiply and divide by rho. So I haven't done anything wrong. So as you can see, here I have rho to k minus 1 times rho, which is rho to the power k, and then I have C rho to the power k, which is nothing but P. Okay? So I can recast this expression in the form dP equal to C rho to the power k, which I call P, then I have k, and then I have d rho by rho. So as you can see, this expression starts to be quite similar to this, and actually it is exactly the same provided E is equal to Kp. So you see, if Kp is equal to E, I can divide left and right hand side by Kp, and I recover exactly this expression. So I've learned that for a gas satisfying this polytropic transformation, I have the bulk modulus, which is not a constant, it is just a function of pressure. Actually, it is function of pressure, a function of the polytropic constant. Now, since the polytropic constant is has this variability, it might be that it depends on the ratio of the specific heats. And the ratio of the specific heats depends on the way the molecule of the gas is done, whether it is monatomic, biatomic, polyatomic, and so on. Okay, now when E is equal to Kp, as you can see, the integral is not is not this simple expression. Actually, it turns out to be even simpler, because what we can do now, we can integrate, assuming that we have a gas, so E is equal to Kp, and then we get V naught. Actually, the left hand side I can integrate right away, so this would be logarithm of V final over V naught, and this one, rather than E, would be Kp. Now K is a number I can bring out, and then this would be minus 1 by K dP by P, which once integrated is logarithm of P final by P naught. But since this is a logarithm, I can absorb this constant into an exponent. Minus. Okay, so I was saying this would be, I was absorbing this pre-multiplicative factor into the exponent, and then I have that the final volume I can write in this way. Okay, so this is how the volume changes when we have a gas undergoing this polytropic expansion, and this is the way the volume changes when we have a fluid with constant bulk modulus, which is mostly a liquid. Okay, so something now I would like to do is to explain why gases mostly behave in this way and why liquids mostly behave in that very different way. As we can guess, this is again something due to the microscopic nature of matter, which gives very different behavior. So let's start from liquids. Liquids are somehow easier to explain. So once again, we resort to the Lennard-Jones curve. So we have, as usual, the microscopic units whose distance is r. Then we put r on this axis, f on the vertical axis, and we have that the Lennard-Jones curve has this shape. So again, these are repulsive forces, and these are attractive forces. Good. Now, you might recall that liquids were those special materials whose units were always at this distance, although they fluctuated so much about the equilibrium position that the connections, the links between nearby units broke and reformed continuously, so that as a matter of fact there was no permanent link among the various molecules, and this allowed the various units to flow. We have also mentioned that the situation is a bit more complex, but for this issue this is what we need. So since liquids are here, at least statistically, now let's see what happens when I try to compress.
So when I try to compress liquids, I would like to force the same number of molecules or the same number of units to occupy a smaller volume. So I'm trying to decrease their average distance. So when I diminish their average distance, in fact, I'm moving in this direction, and immediately I have repulsive forces that generate. On the other hand, if I tried to expand, the same number of molecules would tend to occupy a larger volume, so their average distance would increase. Now, as you can see here, if the displacement is small enough with respect to the equilibrium position, this curve, maybe I could use another color, this curve could be linearized and when I linearize, the force is in fact a spring. Okay? I have repulsive and attractive force which is just proportional to the displacement. And then this is exactly what I get here. I get a constant reaction to the external perturbation, which is pressure, and I get this reaction which is proportional to the input pressure itself. Now, as you can imagine, this is true only as long as I can linearize this curve. So only as long as pressure differences are small enough for this linear part to be used, because as you can see, if I deviate too much from the equilibrium position, the curve saturates, and if I deviate too much to the left, the curve rises steeper than the linear. Now, how can I tell from this relation when the pressure difference is small or big? Actually, you can see from here, this is a pressure difference, and this is a ratio, okay? The ratio with the bulk modulus. So, as long as the pressure difference is small compared to the bulk modulus, then we can neglect the bulk modulus variations with respect to pressure itself. Now, be always suspicious when in science someone tells you big or small without giving you a reference variable. Now here we have the pressure difference, P final minus P initial, must be small compared to E. And E is something that you can find on table. Now for water, you would see that E for water is of the order of 2 × 10⁹ Pascal. So don't forget that the initial relation was something like this. dV by V, which is dimensionless, equal to minus dP by E. Now, since this is dimensionless, this must be dimensionless as well, the right-hand side. And at the numerator we have a pressure, at the denominator we have a pressure as well. Okay? And in fact, this is measured in Pascal. Now, this is 2 billion Pascal for water. So it means that when you try to compress water, even at 10 bars, well, you still have a small enough pressure for E to be considered constant. Good. So we have explained why for liquids E is a constant, and when up to when we can consider this quantity constant. Now, what happens for gases? Now, gases are very different. As I've said many times already, gases are a very different material because they are made by some units, some molecules who move with random velocity. And these molecules are so far apart that they don't feel any force each other. Now, if you look at the gases on the Lennard-Jones diagram, gases would be somewhere here on the right hand of this curve. So let's put gases here. Now we have a sort of paradox, because gases, as you can see, are very far and they don't feel the force, although this curve approaches zero from below asymptotically. Now this implies that the force, if any, is mildly attractive. Actually, it is essentially zero, but definitely it's not repulsive. So if I have a volume like this, containing all these molecules, and then I try to compress, the effect would be to move gases along this line. And when I move here, definitely the forces would be negligible, but once again they are certainly not repulsive. So apparently when I try to compress, there is nothing that reacts against this compression. Actually, if I persist long enough, at some point I will start to enter this region, and this region is attractive. So it seems that I start compressing and I don't feel any reaction because the forces are almost zero asymptotically, and then I can keep pushing, and when I keep pushing the force for a while stays zero, but at some point I should start to experience an attractive force, and then I'm helped by the attraction of the molecules to compress. So apparently, even if I don't do anything, I keep compressing. Actually, the gas keep compressing itself until I don't reach this point. So it seems that I can have some gas in a container. Initially, I have an effortless compression because I don't experience any reaction. And after a while, when I enter this attractive region, I just remove, I take out my hands, the gas self-compresses itself until I reach here, and then apparently the gas liquefies. Now this is of course a paradox. It can be true. So what is missing from this picture? Actually, this picture misses one key element, misses the kinetic energy of the molecules. So as I said, this is the picture that would be true provided each molecule stayed at its position at rest. Now, for liquids and gases, since the kinetic energy, the agitation of the molecules is of course an important feature, but it is small compared to the work needed to break the bonds, I can pretend that this picture applies fully. For gases, of course, it would be grossly misleading. Why it would be grossly misleading? Just because this picture is missing the most important energy source. Actually, there is nothing to break here, so the energy for breaking the bonds is not present. However, the kinetic energy of the molecules is actually all the energy the molecules have. And then I have to complete this picture by another one, which is the Boltzmann distribution. So actually, if I indicate by V the kinetic energy, actually the magnitude of the velocity having each molecule, and I put on this axis, and I can put here the probability distribution function of these molecules, I would get a distribution like this. So, how do I interpret this, this curve? This is the Maxwell-Boltzmann distribution. So the way I should interpret this picture is that each molecule has a different velocity, not only in direction, but also in magnitude. So there might be molecules having a very small velocity, and molecules having a much more intense velocity. Now, if I take whole molecules, and then I start asking what percentage of the total amount of molecules has a velocity in between this value and this value, well, the percentage would be this one. What percentage of the molecule has a velocity in between this value and this value? Well, the percentage would be this. So a curve like this is called a probability distribution function. And of course, if I asked what is the probability, what is the percentage of molecules having a velocity in between 0 and infinite, the percentage would be 100%. So the condition for this curve is that whatever its shape is, the area below the curve must be always 1. Now, if this is the case for gases, we know that gases have all this bunch of possible distributions. Now, let's see what happens when I try to compress. So, let's pretend that this is a sort of cylinder, and here I have a piston. Now, I've said that according to this picture, it appears that when I try to compress the gas, so when I'm moving the average distance from here to other places, I don't experience any reaction. Now, if I try to do this experiment, for example, you take a syringe, you close the final hole and you try to push the piston, actually this is not what you feel. Your perception is that when you start pushing, you can have some displacement, but the more you push, the more it becomes difficult pushing the piston. So what is the reason for this very different behavior? Actually, the reason is that the molecules moving into this volume have some velocity, and some of them collide against the pushing piston. Now, you might recall that a molecule bouncing against a wall transmits some force because of the impulse theorem, and the resultant of all the collisions per unit time against this piston is nothing but pressure. Now, if you try to compress the gas, you try to reduce the space to the same number of molecules. So since the same number of molecules have less space to evolve, you will have more collisions per unit time. It implies that when you try to compress, the more you compress, the more you increase the inner pressure. Actually, the number of collisions per unit time is what from outside, from our macroscopic world, we call pressure. And if you increase the pressure, actually you you make the compression of the medium more difficult. Now, as you can see, this is what we see here. E, which is the resistance opposed by a material to be compressed, is proportional to pressure itself. So you compress, you increase pressure, and you increase the resistance that the medium opposes to your compression. Actually, here there is also a new ingredient, K. So what is this K? Is the polytropic coefficient, P by rho K equal to constant. So this is telling us that when you compress a gas, it makes a difference what kind of transformation you are trying to impose. Now, I remind you that for an isothermal transformation, K is equal to 1. So it means that E is just K. For an isentropic transformation, K is equal to gamma, which is Cp by Cv. Now, if you take care, this ratio is 1.4. So it means that E is 1.4p. So it is 40% bigger than for an isothermal transformation. So what is going on? Actually, when you compress, our experience is that the gas heats up. In case of isothermal transformation, when the gas tends to increase the temperature, you keep the temperature constant. And this can be done by cooling the sidewalls. So since you remove temperature, you remove kinetic energy from the molecules. So the kinetic energy with which they bounce against the piston is smaller. And this is why the bulk modulus decreases. In an isentropic transformation, actually you isolate, you put a thermal insulation about the piston so that there is no heat transfer. And then when you compress, the gas heats up, but it has no way to get rid of the additional temperature. So this implies, we will see that this Maxwell-Boltzmann distribution is such that when temperature increases, the curve becomes flatter and with higher tails. So high velocity molecules are more probable. So when high velocity molecules are more probable, they are likely to transfer more momentum or more force to the piston. And then it becomes harder to compress the gas itself. So, to recap this bulk modulus and compressibility issue, so what we have seen is that when we try to compress a fluid, it changes volume. It can change volume in two different ways. It can change volume by maintaining a constant bulk modulus, and then this is the way you parameterize the volume variation as a function of a pressure variation. Or it can change volume in this very different way with a bulk modulus, which is this expression. And the reason why it has this expression is that a gas undergoing a polytropic transformation has the molecules with some random velocity given by the Maxwell-Boltzmann distribution, and there are no permanent connections among the molecules. Okay. This concludes the first part of this class on the compressibility of fluids. Good. In the second part, we have to discuss the second issue, which is the dependence of density on temperature. So you might recall that before I've said that the density depends on pressure and temperature. And when discussing the bulk modulus, we have seen how density or volume changes with pressure. Now we will focus on another property, which is the temperature dependence of density. Now, you know for sure that when you take a material and you heat it up, it expands. So heating structures or heating a fluid entails a change of volume, and this is somehow intuitive to understand, because when we add heat to the material, it increases the temperature agitation of the molecules or of the microscopic units. And then the result from outside is that we see increase in the volume. Now, from outside, if we just plot the density of some material versus temperature, now since the same amount of matter increases its volume, the density has to decrease. So recall that the density is defined as the mass divided by the volume, or variation of mass divided by variation of volume. And now, since the mass is the same, but the volume increases, now I don't want to get you confused by this data. Let's keep it like this. So the mass remains the same, the volume increases, density decreases. So when you increase temperature, volume goes up, density goes down. And so a typical behavior could be something like this. Why I sketched this wiggly curve? Well, just to stress that there is no reason for this curve to be a straight line. So depending on how the material is made inside, it can have very different behaviors. However, a common feature of almost all the materials is that when you increase temperature, density decreases. So how can we parameterize this behavior? Well, let's assume we have some reference temperature, which we call T. Then what we can do is to make a perturbation of this temperature, either plus or minus, and then we call it dT. This is the infinitesimal temperature perturbation. And then, if I linearize this curve along the tangent, an infinitesimal temperature variation with respect to a density, a reference density, gives another infinitesimal density variation. Okay? And so, what I can do is to write this relation like B rho by rho. So once again, the relative density of variation, and this would be linearly related to the temperature variation. And this parameter alpha, which depends on the material, is called the thermal expansion coefficient, or actually, to be more precise and just to stress that now we keep pressure constant, it is called the isobaric temperature expansion coefficient. So why it is called temperature expansion? Because this expansion implies that when you increase temperature, the material decreases density. So, well, if alpha were a constant, so if alpha were constant, only if, this could be easily integrated between initial and final density. So if this were constant, I could take out of the integral T naught and T final dt, and then once integrated, this would be logarithm of rho final divided by rho naught, and this would be equal to alpha T final minus T naught. However, why I use the hypothetical? Why I say if it were? Well, assuming that alpha were a constant would imply that this was a straight line, which clearly is not true. So, for materials whose density changes with temperature in some difficult way, what we usually do is to approximate the real behavior by a piecewise linear function. So actually what we do, we linearize the curve by some segments, and for each segment you have a different behavior. Now this implies that if you take a fluid like water, for example, what you get is a table like this. Temperature may be in Celsius degrees, and alpha. Now let's see the dimensions of alpha. This is a dimensionless quantity, so this must be a dimensionless quantity as well. So since this is a temperature, this would be the inverse of a temperature. So for example, this could be Celsius degrees to the minus 1, and then you have here, say, 10, 20, 30, of course up to 100, because above 100 you have a phase transition, and here you have some numbers. Now I don't remember the numbers by heart, so I'm not putting any number. However, you can take them from any table or on the web. So this is usually the behavior you have for liquids. All the liquids have a thermal expansion coefficient that you can find in tables. And this thermal expansion coefficient is defined into temperature interval, and these temperature intervals are just the regions where you linearize by piecewise straight segments the actual curve. Then again, what we do for gases? Well, for gases the situation is again different. The reason is that you cannot assume, even for a very short temperature variation, that alpha is a constant. And we can see it very easily. So, first of all, we know that for gases, in most of cases, we can use the equation of state for ideal gases, and then we can use this definition of thermal expansion coefficient. So what we could do is to try to manipulate the equation of state in such a way to recover this expression. Now keep in mind that we are talking about the isobaric thermal expansion coefficient. Okay, so isobaric means P equal to constant. So what I could do here is to recast this equation in this way: rho equal to P by R times 1 by T. Okay? Now, why I put together P and R? Because when the transformation is isobaric, P is a constant, the same as R. Now I can differentiate, because I need the differential, and then I get d rho equal, this is a constant, so P by R. Now I have to differentiate 1 by T. So the derivative of 1 by T is minus 1 by T squared dt. Now, this T squared I can write as 1 by T by T. And now, P by rho T, P by rho T is equal to rho. So I can write this expression as minus rho dt by T. Now look here, I need on the left hand side d rho by rho, which I can get very easily by dividing left and right hand side by rho. So I have d rho by rho, and this would be equal to minus 1 by T dt. Now if you just make a comparison, this one and this one, it is trivial to realize that alpha must be equal to minus 1 by T. And this is for ideal gases. So when you have a liquid, alpha is given in tables like this, and the integration within the piecewise linear function is in this way. Instead, when alpha is a gas, it's not a number, but it is a function. Now, you might notice that this function is minus 1 by T T is the absolute temperature. And as you can see, there is no indication here of what specific gas we are handling. So all the gases obeying the equation of state for perfect gases have the same thermal expansion coefficient. It doesn't matter whether you have hydrogen, nitrogen, oxygen, carbon dioxide, sulfur hexafluoride. Every gas obeying to the ideal equation of state displays exactly the same thermal expansion coefficient. Now, as usual, if we want to see why it is the case, we have to again resort to the Lennard-Jones graph and to the Maxwell-Boltzmann distribution. Now, once again, for liquids, it is quite easy to show. So for liquids, if this is the Lennard-Jones curve, so force R is the distance, so this is repulsion and this is attraction. We know that liquids have most of molecules at this magic distance, but the same argument applies for solids. Okay? Now we know that this distance is the equilibrium distance. However, liquids have enormous excursions, enormous fluctuations or vibrations about the equilibrium position. Now, as you can imagine, let's pretend that this would be the fluctuations about the equilibrium position for some temperature. Now, since each of these units is occupying this region, on the average, the centroid is this one, and then the average distance would be this lambda. Now, let's assume that we increase temperature. Now, if I increase temperature, according to the Boltzmann distribution or according to the microscopic meaning of temperature, I'm increasing the excursion of these vibrations. So rather than staying here, I start to oscillate around this equilibrium position. However, now there is a difference. Now let me try to sketch the linear approximation of this curve. So as you can see, when I try to go to the left, so to decrease the distance, the actual curve increases the repulsion force more than linearly. So you can see that the actual curve increases steeper than the linear approximation. When I try to move to the right, so to increase the distance, the actual curve grows less than linear, and at some point it even saturates. So it means that when these two molecules try to get closer, the excursion increases, but increases less than it would if the reaction were always linearly increasing. On the other hand, when they try to get far apart, the excursion increases more than it would if the excursion increased linearly. So if now you sketch the new envelope of the positions occupied by this vibrating unit, the center is not this one anymore. It will have moved somewhere here, and the same happens here. So I move from a situation in which the actual distance was lambda at a situation, a new one, in which the average distance has increased. because in these fluctuations, the variation is not symmetric. When they get closer, they get less than they should, and when they get far, they get more than they should. And so, overall, the same number of molecules, of units, is increasing the average distance. So the same number of units implies the same mass. Increasing their average distance implies increasing the volume occupied. And so this explains why, for increasing temperature, the density decreases. Now, what happens for the gases? So before I've mentioned that gases are somewhere here, so they don't feel any force from the nearby molecules, except for when they experience a collision. Now, the velocity by which these molecules are animated has a probability distribution function which is something like this. Now, this is the Maxwell-Boltzmann distribution. I try to recall by heart. So let me see. This would be 4 pi. There is a multiplicative coefficient. Then there is some function here. Then we have a squared power of v. And then there is an exponential. And this exponential part is made in this way. E, so here we have v squared, and this would be e to the minus, because it is decreasing. Let me see, it should be v squared by 2t. I will tell you in a moment what is this t. Then there should be m. And here, I remember there was a power 3/2. And then there should be, let me see, should be something like this. 2 pi divided by no, n divided by 2 pi t. So I don't swear on the correctness of this distribution, but if it is not correct, it is very close. So let me specify. What is m? M is the mass of the units moving of the gas. T is the absolute temperature. V is the velocity. Now, what are we saying? We are saying that the probability distribution for a molecule to have some velocity is described by this curve, which has this form. Now, as you can see, there is a v squared here, which is responsible for this parabolic behavior, and there is this exponential, negative exponential part, which is the tail. Now, something very important for what I want to say is the temperature dependence. Assuming that this is the probability distribution for some temperature, what happens if I increase the temperature? I will have something like this. So keep in mind that the area below this curve should be always 1, because it is the probability for a particle to have a velocity in between 0 and infinity, and so the probability is 1. And then what does it mean? It means that when I increase temperature, I have two effects. I move the line, the curve to the right, so I increase the most probable velocity. But more important, I increase the percentage of molecules whose velocity exceeds some threshold. So if I have a box like this, full of gas molecules with some velocity, and then I increase temperature, what happens? I'm moving from this curve to this curve. It means that on average, the molecules will have larger velocities, implying that when they collide against the wall, they will transfer more momentum. Because of the impulse theorem, they will communicate a more intense force. In other words, from outside, from the continuum view, on these walls I have more pressure. The pressure inside the box has increased. However, keep in mind that within this context we are looking at sorry, if I don't refresh the video every now and then, it stops the recording. So we are looking at isobaric transformations. So the only way I have to keep pressure constant if I add temperature is to give the same number of molecules more room to move, so that the pressure can decrease, since in a bigger volume the same number of molecules will have less collisions per unit time against the walls. And then this explains why in a gas, when you increase temperature, you decrease density if you want to maintain pressure constant. Now, what is important to see is that this pressure increase, this density decrease depends on temperature only. Well, maybe these topics could be completed with some exercises that probably we will do in a successive lessons. Okay, see you next time.